That's actually. Yeah. Yeah.
All right, guys. So we should be recording. Yep, we're recording. Share the screen. All right. We're going to continue with the second part of today. Okay. Guys, so my goal is to finish the script, and we are pretty close to it. I know there's a lot going on. If you haven't seen any of this, there's a lot of information. But just as I said, keep in mind, we repeat this pipeline all semester, right? So it'll become more familiar. So I always like to talk a little bit about current news, a little bit. So I didn't know how familiar you guys are with the companies that are AI companies, but I'm sure you've all heard of OpenAI, right? And raise your hand if you've never heard of OpenAI. Anyone here not know OpenAI? All right, so they're pretty important, right? So they're the leading edge company. There's a new one though. It's called Super Secure Intelligence. So it's Ilya Sutsketer's. So Ilya Sutsketer's was the brains of OpenAI. It's like the lead research scientist, and he left OpenAI. And now he created his own company. I think it's called Super Secure Intelligence, something like that. So now we're going to have two companies out there. So it's going to get interesting. Okay. So anyway, you can look it up, but it's pretty, there's a little bit of like, it's exciting also to follow like who the companies are involved in all of this. He announced that he was going to do it like 3 months ago, and then recently he got $1 billion funding. Yeah, just so this $1 billion in funding basically means he's going to steal all the talent from OpenAI, and they're going to go to his company. So, but it's pretty exciting. Anyway, these are, if you like these kinds of things, these are the companies that you can follow, and who are, they're building all these technologies. All right. So anyway, and they build it with PyTorch, so sometimes, or TensorFlow. All right. So let's continue. Okay. So the next, guys, so we're working on the Iris data set. We're building our first model. We're going through the pipeline. At this point, I have my X and Y, and I've said that normalization is really important. And you should make a note of that because it's going to be very basic. Okay. All right. Also, I will say, so my plan is to cover Iris, and then I cover wine quality, and then I'm going to give you a homework assignment for you to create your own neural network. Okay. So you will repeat this, but with a data set. Okay. So that's going to be something, and that's going to complicate things because, depending on the data set that you're using, that's going to determine, your implementation. So pay attention, close attention, but hopefully though, the pipeline can be very similar to this. Okay. Very similar. All right. So I have my X and Y, and I have my X means and standard deviations. Right? And this is the information that I'm going to use, as I said, for standardizing the data, but I haven't done it yet. Usually, one thing that we have available in these frameworks is data loaders. Data loaders are like a construct or an abstraction of the data, and they're very nice. So it's basically, you can think of it as a code wrapper. This happens a lot in deep learning. There's a lot of wrappers around things, so code that takes something and wraps around it and provides functionality that's really nice. So I'll talk a little bit about the functionality. So you can choose not to use these data loaders, but then the problem is you have to implement some of these things on your own. And that's not always easy. So by using these wrappers, everything is done for you as long as you do it in the right format, right? And that's what I'm going to show you is how to create your data. I think this approach is a nice one. It's clear. You can take the data in X and Y as a torch tensor, create a specific data structure that you can load directly into your data loader, and then you can just use the data loader in the training. Does that make sense? All right, as you can see, I have a heading here called data loader. So I'm going to create data loader. All right, so the first thing I'm going to do is I'm going to just look at how many samples I have. So you can see I have 120 samples, right? In this one. So I wanted to see that. So now, if you notice, I'm going to create two lists. One is called Iris train list and one is called Iris test list. So train and test. So train is going to be used to train the model. And then once the model is trained, we can evaluate it on the test set, right? So before we load it into, for us to load the data into the PyTorch data loader, we have to have the right format. If you don't, it's not just magically going to load, okay? So one way of doing it is just to create a nice list comprehension, okay? This is something that should be clear to you. So in a list comprehension, notice here, what we're gonna do is we're just gonna iterate through all the samples, okay? So we know in the train set, we have 120 samples, and in the test set, we have 30 samples. Everyone with me? Okay, so I'm gonna do for I in range of X train shape 0, right? And that just means, I just said that's 120. So I'm iterating through 120, and then I'm just gonna index through, and notice this is really important, okay? I'm going to create a list comprehension of tuples. And a tuple in Python is basically a thing that has values in it, such as 2 values, okay? If you create this list of tuples, then you can nicely just load that into the PyTorch data loader and you're done. Like a very big part of the code is done in just a few lines of code, okay? And then when you have your own data sets for your homework and things like that, take this approach also to load your data, okay? All right, so if you notice here, I'm taking X train TR and Y train TR. So the tuple has to have the vector of 4 plus the class that we're trying to predict on. And you don't even have to one-hot encode it, right? So if you notice, we haven't one-hot encoded the data. That means that I haven't created a vector of 0, 0, 1 or 1, 0, 0. I'm just putting in 0, 1, and 2. You see that? I don't have to do that operation currently, right? I haven't done it. All right, so you can see here, for I in range. So it's gonna 120 indices. So index 0 for the X train TR and index 0 for the Y train TR. And I create a tuple here with that specific format. Any questions? All right, once I do this, I'm gonna have my list, and then I just repeat the exact same process, but for the 30 samples in the test set. So if you notice, X test TR, Y test TR, okay? And once I have that, boom, you can see there, I have my, I just did a slice of Iris train list, just to show you that inside I have these tuples of a tensor of 4 and the values 2, 1, 0, which if you notice, I'm using this dot item. So it's basically like just the integer itself, no square brackets around it or anything like that. Do you guys see that? Does this make sense? And the reason why I'm doing this is so I can have my data in the right format, so I can almost then pass it to the data loader without issues. Any questions on that? All right, so it seems like that was clear. So now I have my list of data. And if you notice, the next step is to invoke torch utils data loader. And that here I will just directly load Iris train list to produce train DL, where DL stands for data loader. And once you do that, you've done a lot, because the nice thing about this is when you create a data loader, you can define the batch size. So what that means is you're going to say, okay, I want my batch size to be 16, right? So whenever you're iterating through the data loader, it'll just grab the 16. You don't have to like pick starting point and ending point and slice it and all that. So all that code is done for you inside. Got it? Another thing that's really important, if you look over here, it says shuffle equal true. This is critical. It's something that you want when you're training your models. Every time, every epoch that you give the data to the model, you want to shuffle it. So you could shuffle it on your own, but then you'd have to write that code, right? By doing it in the data loader just handles it for you. Got it? So I usually, whenever I have a problem, whatever the data is, I will take the extra steps to format the data in the correct way so I can use data loaders and then offload a lot of work to this very efficient construct. Make sense? All right, perfect. So if you understand that concept, that's really great. So I've created my train DL now. That's there. I do the same for the test set. Notice it's exactly the same thing. Invoke data loader on the Iris test list, and I create test DL. And now I will have my two data loaders over there, and you can see when I print data loader here, it's like a torch object, basically. So it's got this wrapper around things, okay? A lot of wrappers, when we start using frameworks like Hugging Face, that's like a wrapper around all the torch wrappers, right? So it's a lot of that. All right, so hopefully you're excited. So if you've never done a neural network, you're about to do your very first neural network. And hopefully by the end of class today, you will have done deep learning, right? And deep learning is actually a pretty straightforward concept. Okay, I think we covered it a little bit in the lecture. And if you read what I provided for you, it should be very clear there, right? So deep learning is a term coined by Geoffrey Hinton, and he basically just said, more connections in between the inputs and the outputs makes it deeper, okay? So I'll show you how to create one. I definitely recommend, even if you took object-oriented programming a long time ago and didn't like it, and whatever, definitely I stress refresh that knowledge, because this will make your life easier. While you don't have to use object-oriented programming for something as simple as the Iris neural network, as we move really fast in this course, things will get big, right? There's going to be an object-oriented is essential in modern deep learning, okay? Because it just makes your understanding of things way easier, okay? So make the effort. All right, so I'm not going to go over what a class is. However, in the notes that I provided somewhere, here, if you go back to, I think somewhere in here, like data loading or something like that, there's a little bit in there about object-oriented programming. And so read through that, please. Okay. Anyway, so everything is going to be very much like a template that we're going to follow. So to define our architectures, we're going to basically, use object-oriented programming. So here you can see I have a class called MLPNet. And then I should have another one called DLNet. So I create these classes basically, okay? And we're going to take this approach all semester. And it just makes, it's basically our neural networks are going to be self-contained as much as possible within these classes, okay? And it just makes it easier, all right, to understand. All right, so let's go ahead and drill down into one. Okay, so I'm going to create this one, class MLPNet. Notice that we're going to use class inheritance, which basically means that we're going to provide nn.module. nn.module is the PyTorch generic neural network class. We bring that in with all its functionality, and then now this class effectively has all of that available, okay? And then we just have to specify a few things for our specific architecture, okay? Yeah, all right, so the first thing so notice that two functions will be here initially. Later on, as we start to maybe look at generative models, we will have a third function in there called generate, something like that. But for now, we're always going to have two functions, which are this one, def init, and this function, def forward, okay? So these are basically, so the init is the constructor. We're going to initialize our objects. And then in forward, we're going to build our neural network pipeline architecture, which basically will have an input and an output and the operations in between. Got it? Okay. And there's 2 or 3 different ways of doing this. I will show I like this way, except like with CNNs, I like another approach because CNNs are a little bit more verbose. But in this example, this one is the more intuitive for me. So I'll start here. All right, so I'm not going to really talk about like linear, nonlinear right now. I'm just going to dive into this. But later on, as we progress, you'll start to see the differences, okay, of what everything means. So here, let's take a look at init first. So in init, notice that, well, the self, Python needs to have that. But notice here, we're saying that we have 2 inputs when we initialize our model. And those inputs are actually x means and x deviations. We've already calculated these, and these are for normalization. The reason why I put these in here is because sometimes you need to deploy your architecture, right? You need to deploy your model like to the web or something. And if your model normalizes the data, how are you going to do that on a web page? Do you see that? So it kind of has to be in the architecture itself as you do it. Okay. So that's why these are going to be here. Guys, question? So then we do the super here, and this just initializes the inherited class. And then after that, I'm just going to define some of the objects. Again, this is all very new if you've never taken this course. So, but it'll get very repetitive. So you'll start to see what everything is. Okay. So the 2 x mean and x deviations that we calculated are just saved into these variables x means and x deviations in the class. And then after that, notice that I'm going to define linear 1, act 1, linear 2, act 2, something called dropout that will, again, it's another there's many concepts. So we'll have to define, find time to define all of these in a little bit more detail. But for now, I just want you to see these pieces and how they fit together. I'm trying to keep this as simple as possible. All right, so basically, NN linear is the basic operation in tensor, in PyTorch. All right, it is your y equal wx plus b. That equation, y equal wx plus b, is this. Okay, if you've gone through the 109 operations that was discussed there, so hopefully you have done that. So basically what this means is NN linear is that it's going to map a vector of 4 to a vector of 3. It's the direct connection from one layer to the next layer. Okay, does that make sense? This is how you start to define neural networks. Okay, this is how you start to define neural networks. Activation functions are one of the things that makes functions go from being linear to nonlinear. This is another concept that's really important. But think of it right now as a transformation. So for instance, the classic thing that we all know, sine, right? Sine and cosine. Takes a value, produces another value. Do you see that? So we have many of those types of functions in deep learning. Sigmoid is one of them. We'll define that too a little later, okay? And then here, there's another linear 3 by 3, as you can see. There's another function called softmax and so on, okay? So I will probably need to take out my whiteboard for this. But so just think of it as we're defining some parts here, okay? Then in the forward function, perform the inference, it's where we're going to take these parts and put them together to create an actual neural network, okay? An actual neural network. So if you notice here, the forward takes in X. So what is X? X is going to be the input that goes into this neural network, okay? So what are we trying to do with Iris? We were trying to predict if a flower is setosa, virginica, or versicolor, right? So we give it a vector of 4, and it should tell us something about, you know, what that flower is, right? So that's your first X. That's the data. If you notice, X then goes into linear 1 and produces X. Do you see that? So what is linear 1? It's this one here, which these numbers are really important, right? So they're specific to the problem, and it's something that we have to understand. That's why it's nice to start with Iris, because Iris is easy to understand what we're looking at, right? So, you know, 4 is the number of features, 3 is the number of classes, for instance. Once X goes through linear 1 and it produces a new X, and then that new X will go through activation 1. That will be modified based on the logic of something called the sigmoid function, and that produces a new X. And then if you look, this new X then goes through linear 2, and that produces a new X, which will go through activation 2 to produce the final result, which is Y prep. Do you guys see that? Okay, so I should have set up my whiteboard. Forgot about this part. Give me a second. All right, so let's hope this whiteboard works. You guys are seeing this. Okay, so I'm gonna switch to the whiteboard. Remember this code, okay? Because this is the neural network, okay? And what I'm about to do is draw it. So what I have to remember, it's an MLP for Iris. So hope, you know, and then tie it to the code. So to do this. Full screen. This should be. Okay, all right. So it's working, right? So, okay. So let me change. Let me erase this. Okay. Pen. Change the color. All right. So what was I doing, right? So in that architecture, I had linears, right? I said NN linear. So NN linear, if you don't know, in the past, when all of this started, there was no NN linear. you actually had to declare your own W, your own X, your own B and everything. And guys, shh. All right, so you have to declare all of this. But what I want you to understand is that NN linear is yet another wrapper, right, around more basic things. So in essence, NN linear is that equation, which is the fundamental equation, if you will, in neural networks. As you start to build ever more complex architecture, right? But that's what this is. NN linear is basically that, with the advantage that you don't have to define W and B. They just exist within it, and they're called parameters. Does that make sense? So that's one really nice, neat feature of that, okay? So you have to think of this relationship. So then you saw that I created something called linear one or something like that based on this NN linear, okay? So NN dot linear, and I said that it was 4 by 3, right? That was the first linear one that I created. So how does that translate into a neural network? Well, we're saying, because that's the starting point, I can actually draw the neural network. 1, 2, 3, 4. What I'm saying is that 4 for linear one is the input to the neural network. And I'm also saying that I'm going to map that to 3. Exactly. So you can see I'm starting to create this architecture of the neural network by doing that and that linear, basically. Okay, so the equation would be X goes in here. This is X, right? And then you produce Y, which would be this one. However, because this is not the final output, it's going to be more convenient to write it as you see that? And then the final output is going to be written as, do you see that? These are basically the underlying equations that are being done by this linear one and linear two. Do you guys see that? So linear one is the first one. Okay, so it goes from 4 to 3. And then the second one goes from 3 to 3 because we have 3 classes. And effectively, we've defined the architecture of a neural network. Is it a deep neural network? By definition, this is not a deep neural network. It is, multi-layer perceptron or whatever you want to call it. Deep would mean it should have at least one more layer, as in general people think about these things. Does that make sense, guys? Okay, so maybe I can switch back and forth. So hopefully this is, you can see that by establishing these linear functions in there in sequence, right? I am basically creating the neural network. There's several assumptions here, like it's a fully connected network, okay? And so on, fully connected and all that. Okay, and the same applies over here. All right, so let's go now back to the whiteboard. So I'm going to go back to the code. All right, so we're back at the code, and you can see here in order then we have X to X, linear one, right? So basically we said this is four features that get mapped into 3. Ignore this part currently, right? And instead just assume the next layer is X goes into linear 2, and you can see that linear 2 is 3 to 3. Do you see that? And you can, if you said that this is 6, then just make sure that this one is also 6. Okay, you can define the architecture as you'd like. However, what really is important is this you can't really change because it depends on the features that you have in your data, and this will depend on the classes that you have, the outputs. Any questions on that? Pretty clear, right? All right, great. So Now this function in between the activation, in this case, we're using this function called the sigmoid. Okay, so I'll talk a little bit about it at this point. I'm going to go back to the whiteboard. I'm going to do this. All right, so the sigmoid is a function that maps values. So if you think of this as 0, right, and this is minus infinity to infinity, it should do, and this should be 1. It basically should be something like that. Do you see that? So it's doing what? It's taking values, maybe minus 1,000, and this one is like plus 2,000 or whatever. But the values go into the function like this, and they will come out as being between 0 and 1. Do you guys see that? Does that make sense? That's what these functions do. It seems trivial, but this itself is what creates these things called nonlinearities. It's like you have to think that you're giving the network something else that it can do, right? To understand things a little bit better, okay? To create better interpretations. But anyway, so when I give it the data, X, it goes into that activation, which is a sigmoid. And, you know, let's just say X comes out. Oops, it's doing that thing. X comes out, and it's been modified, okay? From, let's say, minus 1,000 to maybe, I don't know, I'm making something up here, but 0.20. Got it? Got it, guys? Any questions? And just keep in mind, there are other activations, like something called ReLU, GeLU, TANH. Well, so something interesting, for instance, is transformers. My understanding is they shouldn't use TANH activation functions. It just doesn't contribute to learn. Whereas they have, you know, based on experimentation, they have determined which activations actually are more helpful for the transformer to learn. Okay, so these choices that you make are really important. For Iris, it doesn't matter almost, but for other ones, it will. Okay. If you go through the notes, as I said, you'll find more discussion on these topics. Okay, including the softmax and so on. But anyway, this should give you an intuition. All right, so I definitely want to finish your first neural network. So let's get to the end of it. And as I said, there's so many concepts, right, that we're learning, but hopefully, as we proceed throughout the semester, things will become clearer and clearer and clearer. As this is, this is the basic pipeline that we will follow all semester. All right, so I'm gonna close this out. And I'm gonna go back to sharing the screen. All right, so I think now we can start to move on, right? So I've done this architecture. So remember, this is a multi-layer perceptron. I have one input layer of 4, a hidden layer of 3, an output layer of 3, okay? That has been defined. There is an activation function after the hidden layer called a sigmoid over here. There's another one called softmax. This is an important one. I'll just say for now, similar to sigmoid, I'll come back to this idea later, okay? But think of it right now as it's mapping to values between 0 and 1, where they add up to 1, basically. So it's a type of a probability distribution. And then this dropout, I'm not even using it right now, so let's ignore it, okay? We'll come back to it. It also is useful. Got it? All right, so this defines the architecture right here. X goes in through all of these, and then you get Y pred. And that should be your result. which should be a vector of size 3. Okay? All right. So now I'm going to go ahead and run it. So you can see that's run. All right. Now I have another architecture. And this one, if you notice, says deep learning with 2 hidden layers. So in the first one, it wasn't deep learning because I had input, hidden layer, output. In this one, I'm going to have input, 2 hidden layers, output. Does that make sense? And just that creates a deep learning model. Questions? All right. Same idea. I create my class, DLNet. NN module is the inherited class from Torch. X means and X deviations. This will become useful later. The constructor, it initializes the inherited class. I assign X mean and X deviation to the internal variables of the object. And then these are the 2 functions, init and forward, okay? So in init now, this is where I start to define the constructs that I'm going to use to build my neural network. So you can, think in reference to the previous one and now think this one and try to create that neural network, like draw it out, okay? So think about it. Linear, right? NN linear. Remember, that's your y equal wx plus b. So 4 input, right? 4 parameters. Notice that now I've changed that to 15. Why? Because here I have a lot of freedom. I can make, pretty much whatever I want. This is called the architecture and you're the architect. Okay, so in a lot of these, you can do whatever. In things like GPTs and transformers, you almost never touch it. Like you literally just use as is. If you think about it, actually the transformer, believe it or not, created in 2017, and what they're using today is almost exactly the thing that they did in 2017. It hasn't, the architecture itself has not been modified that much, right? Which is amazing. All right, so anyway, so you do 4. Imagine you have 1 layer of 4, then you have a layer of 15. So that, then you're going to have these, instead of sigmoids, you're going to use ReLUs, another type of activation that we can discuss. Now I have linear 2, linear 3. Notice that the output of linear 3 is still 3, right? So that the input and output have to be the same, but the hidden layers in between can be different. And I still have a softmax and a dropout. So now let's take a look. This is a more robust, if you will, neural network, right? Because it's got better mechanisms. You can see that here I am using dropouts when I need to. I'm using different activations and so on. Okay, so this is what I'm building. So now let's draw it out, right? So that we can get a sense of the neural network that I'm building. So 4, 15, 9, 3. Okay, so I'm going to switch to the whiteboard again. Nope. Okay. So once again, this neural network that I'm building, right, was, I'm just going to draw like the parentheses, right? So it's 14, comma, was it 15? 15. Then the next one was 15 to what? 9. Okay. And then the next one was what? 9, 3, right? Okay. So what does that look like as a neural network if we draw it out? There's 1 hidden layer. Oh, sorry. The first layer is the input. It's got 4. Do you guys see that? The next layer is 15. So these two have to match, right? Because you're going from this one to, it's like you're saying, map it or transform it to 15. And then in the next one, you say the input is 15 and transform it to 9 and so on, right? So you're kind of doing that. So the architecture then here, so this is 4. This one is 9. Oh, sorry, 15. So 15. The next one is 9. And the last one is the same 3, the output, the 3 classes. Does that make sense, guys? So these usually, you want to name them as hidden 1 and hidden 2. They're just the hidden layers, as they're called. And that's it. That's your first, if you've never done learning before, this is your first deep neural network. What makes it a deep neural network? It's got to have more than one hidden layer. And it's got to have activation functions. If you don't add activation functions, it's still what is called a linear model. So it won't have the power of a, that we expect from neural networks, because they need to have these activation functions. Any questions? Is all that clear? Do you understand the relationship between the networks and how to code them? Pretty important, right? So we will be doing this a lot, and just keep in mind, it's going to get, this is actually where, like this space here is where it's going to get elaborate, deep. This has 2 layers. ResNets, I think the very powerful ResNets, they have like 150 layers. And they're not just like normal layers, they're 150. I don't want to say that all are convolutional layers, because they aren't, but a lot of them are convolutional layers, which is a complex type of a layer. And then usually like the last 3 or 4 are normal layers like these. Okay. So anyway, they can get very deep. Okay. That's, and there's a lot of power that you get by having very deep neural networks, especially if you have a lot of data and so on. Make sense? All right. So we've defined the architecture, 4 by 15 by 9 by 3. So the last one is 3. Okay. So I think we can go back to our code now and should be pretty close to finishing our model. So close the whiteboard. Share the screen. So we're back to the code, right? So here it is, 4 to 15, 15 to 9, 9 to 3, activation functions in between. All right. And that's it. So now let's get to the next part. This is the training loop. If you notice, it's a for loop, right? It's a function really, but with 2 for loops in it. And this is where we're actually going to do the heavy lifting and train our model. I like this approach. There are other ways that you can code this, but I just, it's kind of my preference. A lot of people use this approach. All right, so we define the function, and then over here, we're gonna define some things, and then down here, no, actually here, we're gonna invoke that function. All right, so let's take a look at the function. So the function train loop takes n epochs, which we define at the parameters, about 4,000. Takes model. What is model? It's the class that we define. We have to instantiate it and pass it to it. The loss fn, that's the thing where all the math happens, right? All the calculus and all that stuff happens there. And an optimizer, that's where it happens. And then loss fn is the objective. Okay, so we're gonna look at that as well. All these 2 items, they're like chapters in a book. Okay, so there's a lot going on there, right? But for now, we're just gonna use them. Okay, but as I said, models are architecture usually, the loss function, the data, and this is kind of like the heavy lifting is done by this. Okay, the optimizer. So we'll get to those concepts. All right, so we're in the train loop. So what needs to happen is we have 2 for loops in this case, right? 2 for loops, if you notice. The first for loop is pretty easy to understand, I think. For epoch in range and epochs. So what does that mean? Repeat this 4,000 times, right? This is what I said in the beginning. You grab all the data 4,000 times and give it to the model. Okay? Like all of it. So that should be clear. This part is where all that train DL becomes really helpful, because if you notice, now all we have to do is for X, comma, YB and train DL. So basically we're training, the B stands for batch, because we batch the data. So we're going to take a batch of X's with their corresponding batch of Y's. So that's like saying 16 by 4, right? 16 rows of the petal length, petal width, petal, all those 4 variables and their associated class. So this vector is a setosa, this vector is a virginica, and so on, right? We give that information into the neural network. So we grab that from the train DL. Model, as I said, is those classes that we define. They get instantiated over here. So we give XB to the model. Do you see that? It's like we initially, model can predict, but it's going to do a bad prediction. Do you see? Because it hasn't trained yet, so it doesn't know what to do with the data. That's what it has to learn to do now, okay? But we already have an architecture that you give it a vector of 4, it'll give you a vector of 3. It's just going to be a really bad vector. So think of it as if it was generating images, right? So you give it some information initially, and it's going to give you just noise in the image. As you train, you would give it data, and then it's going to start looking like a cat or a dog or something like that. All right, so here we do XB. These are the inputs. They go into the model and predict Y pred. Then we have this thing called loss FN. So loss FN will take the predicted values and the real values, which are in YB. Because remember, this is the training data, which has samples and their corresponding class, right? The features and their corresponding class. So this is always what we do, okay? Model initially has bad weights, receives X, predicts Y pred. Y pred is compared to Y real in some kind of a function called the loss function. Okay, and that's another concept that's going to take a while for us to grasp. Okay, but we will get to it. There's really not that many loss functions. Actually, you can pretty much say there's only 2 in essence. So and then variations of those, right? So we'll talk about that. But if you want to start learning about this, go ahead and read the notes I gave you. It's covered in there. All right, so once we have Y pred and YB, you're comparing. So how can I give you an example? Let's take this example. I have the model, you give it some data and it says it's setosa, a 2. But it was actually virginica, a 1. So it predicted 2 and it was 1. So that's an error. Do you see that? Next time around, you gave it an X. It predicts setosa, a 2. And it was setosa, a 2. Match. So the loss FN in one example would get 2 and 1. That's an error. And in the other one, it would get 2 and 2. You see that? And it just needs to learn how to minimize that error, basically by adjusting the weights. So this is the relationship that's happening, okay? So think of it like that. So you give it an input, it predicts something, that predicted output is compared to the real, and then you measure it as a metric. And you use that metric to adjust what is called the weights of the neural network to do a better prediction. Do you guys see that? So when you do this part, it's good to have it like a very simplistic, like here, right? So this function, give it the real inputs, predict, compare to the real, calculate the difference, basically, and then use that information to adjust the weights. The beauty of this approach is that you don't have to do anything except give it these 3 lines of code here, okay? And it's going to do it for you. All right, so you can see here we have once you have this loss calculation, right? Then you're gonna do, I'm gonna skip this line for now. And then I'm just gonna do loss backward, right? Given that information, it's gonna calculate the gradients. And basically what that, it does all the math, if you wanna call it like that. And once it's got all that math, it takes a step. And when it takes that step, it adjusts the weights. So one very simple way of understanding this is, think of it this way. I have a value, right? Currently, I have a value. And I want to know, do I add to it 0.05 or do I subtract 0.05? That's it. So loss backwards says add. And now in op step, it adds. You see what I'm saying? So imagine the value was, for whatever reason, 0.8. Okay. Subtract 0.05 from it. So then it's going to take 0.8 minus 0.05, and that's it. That's very simplistic, but that's kind of what's happening. Okay. And again, this is a very complex process that is simplified, and it's actually the reason why we use PyTorch and TensorFlow. Okay, because if you had to code this from scratch, it would be quite challenging. Plus, doing this really quickly and so on. Think about it. You know, when they say 70 billion parameters for Llama or whatever it is, GPT-5, all those parameters, 7 billion, have to be calculated in this operation here efficiently, right? So this is not something that anyone can just do from scratch. Okay, you take advantage of PyTorch, which is optimized to do this for you. Does that make sense? Okay. All right, so hopefully it's starting to make sense, okay? But basically, this is where the magic happens, okay? So if you remember, I said linear was y equal wx plus b, right? We give it x, and we need to know that w and that b. So y equal w times x plus b. We don't know what those parameters are initially. But as we do this process, those are the parameters that we're adjusting so that at the end, we've got w and b. Do you see that? So for instance, if you guys were building a neural network to predict the stock market, right? You know, you don't know anything, but after you've trained, you make a lot of money in the stock market, right? And then Noah here wants to buy that from you, right? What do you sell to him? The W and the B. Do you see that? That's the one thing he doesn't have, because that W and B can only come after training. Do you see what I'm saying? Those are the very valuable. That's where the value is. That's the secret sauce, or the secret in any neural network, these weights or the parameters. Anyway, hopefully that made sense. So I'll repeat it one more time. The training loop basically takes in from the train DL, the inputs and the classes, the real ones that it's using for training. It runs the features through the model. The model is not very good in the beginning, but it predicts something, a Y pred. Sorry, what did I do? Anyway, yeah. So it takes in XB through the model, predicts Y pred. Then those predicted values are compared to the real through something called a loss function, which you define. And then given that value loss, you perform these operations here to adjust the weights in a loop. Okay, so you're going to repeat that in a loop. And eventually what you're doing is what is called optimizing the problem, minimizing the error, and so on. Okay. This function here is just printing the loss every 50 epochs. I skipped this one initially, but basically this is like a weird thing that Torch has, that it accumulates. So the weights and the parameters. So what you have to do every iteration is zero it out instead of accumulating it. And this is just like a mechanical thing. All right, so I'm gonna go ahead and run it now. Okay, no error, I think. And then we're almost done. So now what you have to do is instantiate the model, which is just the class we defined, create an instance of it. We had already calculated X means and X deviations, although I'm not using it for this problem. Then you have to initialize something called the optimizer, which in this case, we're going to use torch optim atom. So this is the mechanism in torch that will do this for you. You give to the optimizer the learning rate, which if you remember, we defined as 0.01 or 0.03. And then notice here, we give it model.parameters. What are we giving it? We define an architecture here, right? The architecture, 4, 3, 3. And the parameters are the weights and the biases, right? So those parameters are here. Another way of saying it is if you wanted to sell your stock market model to Noah, you sell a model.parameters. Make sense? But you're passing that to, I like this part actually, because it establishes a clear connection between the model and the optimizer, right? So I like this. Sometimes this is more abstracted in other language, in TensorFlow and Keras and things like that, and I really like this part. All right. This part I'm just gonna mention briefly because it's a bit complex, but it's we're gonna, since this is a classification, we're going to use cross entropy loss. All right. I have to spend like an hour discussing what cross entropy does. All right. But just keep in mind, this is the loss function that compares in a smart way the predicted versus the real. Okay. And if you want to start reading through it, you can in the link that I provided. And then finally, you have all the pieces, the model, the optimizer, the loss function, and you run them in the train loop and you start the training.
Wouldn't you also pass the data?
It's kind of a global variable. So if you look at yeah, it's not like a totally modular. Yeah, so train DL is treated as a global variable. And that's it. So as you can see, the model is doing its process. So this is printing the loss. So 1.0, then 0.7, down here is 0.55. So the goal in machine learning, the vein of your existence, you know, like the main problem is that you want that to go down. And this is going to give you a hard time sometimes, right? When you're, you know, when you have new problems or a challenge, etc. But it's a good, you know, you want to minimize this loss. A way of thinking about it is you're minimizing the error. Do you see what I'm saying? So your model was predicting always on average 10 and the value on average had to be 3. So it's a big error. Versus once it starts to get good, it's predicting 4 and the value is 3 on average. So it's better. So the loss should be going down. And I'm doing 4,000 epochs, I believe. So we're going to give it some time. I'm also doing the multi-layer perceptron, not the deep neural network. So will the deep neural network do better? Keep in mind, I didn't normalize the data really, so that could affect performance. One thing I can say with Iris is that the results should be pretty good because it's an easy data set to look at. Does that make sense, guys? But we're almost at the end of the pipeline. So here, okay, we just finished. So now, in theory, you have a trained neural network, okay? You should have a trained neural network. This function, I have some slides that we need to cover later as far as the performance metrics. Obviously, we need accurate ways of measuring the performance of our model. So you can just use this function as is. I will describe it later, but we're going to use this to measure if the performance of our model is good or bad. Do you see what I'm saying? So let's just run this function. Oh, yeah, I was already. Okay, so I ran this function and then, so I ran this cell. Okay, so what is this? So if you look, this is a little bit similar to this training loop, but it's the loop for the test set, right? So we want to measure the performance of our model. Do you guys see that? So notice a couple of things. I have this thing called with torch.noGrad. Every time you like give data to the model, it wants to update the weights. But when you're doing the test set, you don't want to update the weights, right? You don't want it to learn because that's, it's the test set. So by doing with torch noGrad, basically you're telling it, okay, in this block of code, do not update the weights. Does that make sense? So it's just a mechanical thing. Then if you notice, since we created a data loader, then that means that we can conveniently just use a for loop. So I can say for x real, y real in testDL, right? And now I'm going to, it's kind of similar. I grab x real, which are the inputs, run them through the model, and I get y pred. Does that make sense? I have a trained model right now, very good at whatever it is. I give it the test data. We had 30 samples, right? 30 samples. And it predicted 30. So for 30 flowers, it told me if they are setosa, virginica, or versicolor. Okay? Once I have that, I'll skip this part for now. But basically, so because this is more of a mechanical thing, but basically, those are the preds. So I should have 30 preds. Yeah, that's 30. So 30 predictions, right? And I had the 30 real values. Do you see that? So I had 30 flowers and I knew what they were. The model also gave me its predictions and now I can compare. Okay, so that's what I'm about to do. So here, I give it X real and I know what they are and Y real. And I'm going to compare Y real to the Y pred or the preds after a little processing that come out of the model itself. So now I give to print metrics, which is this function over here, Y real and the preds, and it just printed out all this information here. And this is the thing that, in a competition determines who wins. Okay. Or this is the thing that tells you, okay, you go to your boss and you say, I built a good model. Or, whatever, or, your company, give us money, we can solve that problem that you wanted us to solve. Do you see what I'm saying? So so the question now is, how do you interpret this data? So this part, Torch Max, what it does is, remember that we did a network that takes 4, some layers, and then it gives 3, right? But then out of those 3, we have to select the index of the highest value. And that's the class that we select, right? So that's what Torch Max is doing. So for now, it's just a post-processing to actually select the index of the class that had the best probability. So we'll come back to this idea a little bit later. But anyway, so the key that I want you to focus on is, how do you measure performance? So we've got how many metrics here? We've got F1 measure, recall, precision, and accuracy. And then we have something called the confusion matrix, okay? Which is this little matrix over here. So all these metrics are coming from the confusion matrix, by the way. This is a lecture that we'll do later, all right? But they're all related. Now, the reason why we need multiple metrics is that sometimes accuracy can be misleading, okay? So you might get a really good accuracy and you think that your model is really good, but actually it turns out it's not that good. So that's why you want to look at all the other metrics. However, in this particular case, the data is so easy, right? And so consistent that they're all basically the same. But this doesn't always happen. So the score goes from 0 to 1, where 1 is like the best, right? So the interpretation would be that if you had 100% accuracy or 1.00, it predicted out of the 30, it predicted all of them correctly. Do you see that? That's it. So in this case, it's saying that there were some misclassification. That's where the confusion matrix is really nice, because it actually helps you to see where the misclassifications happen. Okay, so I didn't label these, but you can assume these are setosa, virginica, versicolor, right? And it's telling you. So obviously, this is setosa, so this should be setosa. This is virginica, so this should be virginica. This is versicolor, so this is versicolor. So that means that you would want all the values in the diagonal to be high and off the diagonal to be zeros. When you have a value off diagonal, it means what? A misclassification. Do you guys see that? So for instance, this one was not misclassified, right? There were 9 of this class and all were classified in that class. But here, this class had 13 values. 12 of them were correctly classified and 1 was misclassified. Do you see that, guys? And then in this last one, it has how many? 8. 8. And out of those, how many were correctly classified? 7. How many were misclassified? Exactly. This is how you interpret the confusion matrix. This is really useful, right? And a very powerful tool. And like I said, this is for classification problems. For regression problems, we'll have other metrics. If we're doing higher level problems like translation, we'll have the blue score. If you have, you'll just have, as you add more problems, or you make your neural networks more powerful, solving more complex tasks, they will have more specialized metrics, right? So Noah's working on solving math problems, right? That's, how does he measure a model that does that? It's, it's a difficult, it can't just use something like this. So it's more elaborate set of metrics. Do you guys see that? Stable diffusion, right? You generate a cat on the moon with a hat. How do you measure that? I mean, a person can look at it and say, that's really great. But is a human going to look at 1 million images? Not really, right? And so but then how do they know? How does Google know, or whoever created Stable Diffusion, Anthropic, I think, how do they know that they built a good model? How do they get more money to fund their company? They have to provide these metrics. Got it? All right, so I think that completes the pipeline. We do have 11 minutes, so I'm going to repeat this. You can see that the Jupyter is almost over. I'm just going to repeat the process, but now I'm going to instantiate deep learning, right? Now, deep learning may be better or maybe not as, it's not magic, right? You have to work at these things, right? So, I'm going to throw deep learning at it, but I haven't done normalization, so there may be other additional tweaks that I have to do to the code. But for now, notice how simple it is, right? If you follow this pipeline, this is what's so great about it. You can run multiple architectures and everything works, right? So if you notice, I did my multi-layer perceptron, good model, 93%. So, but you want 100%, right? Because if that's money, maybe you're leaving millions of dollars on the table, right? So you want to go in for better. So now, how do I run the other one? Well, because I followed my object-oriented approach, I literally just have to change where initially here we were doing MLP net. Now I'm changing that to DL net. That implies that now I have the architecture with 1 input, 2 hidden layers, 1 output. Does that make sense? All right, so let's go ahead. And then notice the optimizer is the same cross entropy, same train loop. All right, so go ahead, run it. Okay, there it goes. So we have to let it train for a while. You can look at the loss function. So I remember the loss function was 0.55. That kind of got stuck there. So this is where you get in, this is where you actually start to do work, right? So you're gonna try different techniques, different experiments, add different things to make that loss function go down somehow, right? So that gives you information that your model's learning, that it's improving. And then, of course, once the model is trained, you're going to check performance once again. You can see we're training. We have to give it, wait, this is going to do 4,000 iterations. But it seems to get stuck at 0.55, right? If you notice, it's not really, it has a hard time. So this is where you have, this is why you need to learn other things in deep learning, right? So that you can try other things. For instance, a different activation function, etc. All right, so let's just wait. All right, any questions so far, guys? We're almost done. I don't remember if it's better or not. Check the GitHub. Maybe that had better results. But I can tell you that Iris should, you should be able to get like 100% on it. Because it's an easy data set. Any questions before we wait? Could also give it more epochs, 10,000 epochs.
Doesn't seem making much of a difference.
Yeah. Yeah, I mean, you can try lots of things. I mean, it could be a deeper architecture. I mean, lots of things. Normalization might be a good one. Okay, so keep that in mind. All right, so I think it finished. So let's see the performance now. Pretty much the same code, right? So same test DL, the data loader. I grab X real, I grab Y real, I give it to the model. Remember, this has good weights now. The input goes in, predictions come out, compare the predictions to the real, and print out the metrics. So let's go ahead. 93, so it didn't improve. I'm pretty sure you can improve it. Let's see, let me see if I did the... I did normalize it actually, because this is the normalization operation. All right, I'm not gonna make this a homework or anything, but if you want to improve it as much as you can, play with it. All right, it's not a homework assignment though. But anyway, that's it. That completes the overall pipeline of deep learning. So this is your basic neural network. You did a multi-layer perceptron and you did deep learning, okay? With Iris. Strong recommendation is just go through this code, especially if you've never done this before, repeat it, type it up. That's your homework. Just do this a lot. Next week, I will go over the wine quality data set, and then we'll do a regression and classification with that one. Please read the notes that I provided. There's so much information. I can't cover everything, but if you read it, you should be able to get a lot out of it. And after the wine quality, we'll start with CNNs and autoencoders. So we're going to move fast. So make sure you do this. And then there will be a homework assignment after wine quality. All right. All right, guys, we can stop here for today, and I'll stay for a few minutes if you have any questions. Otherwise, see you next Monday.
There's no homework